Hello, this is Team Underdog. We are presenting our AI-powered personal beauty advisor as our 2025 graduation project. In today's world, fashion and beauty extend far beyond appearance. They have become powerful tools for expressing individuality and identity. One of the most popular methods is personal color analysis, which recommends colors that harmonize with a person's natural features. However, the traditional system has clear limitations. It relies heavily on subjective expert judgment, can be costly, and also, physical try-ons are time-consuming and limited in scope. So, how is personal color traditionally determined? The conventional method is called armchromia, which classifies people into 12 seasonal types, such as spring, summer, autumn, and winter. This approach considers the contrast of the overall face. Since it deals with the overall face, there is the problem of losing relevance when the user wants to change their lenses or hair color. So, we come up with a brand new personal color system. Instead of relying on the overall face or subjective judgments, our system focuses solely on skin tone. We use K-means clustering to group similar skin tones into clusters. This gives us a much more stable, consistent, and practical base for making recommendations. Unlike the traditional method, our system adapts better to changes like hair color or lenses, while still keeping the core skin tone as the anchor for color harmony. Our system is trained on about 5,000 images from the armchromia dataset. But raw images come with big challenges. Many are overexposed, underexposed, or distorted by lighting. So, we built a data preprocessing pipeline that corrects lighting adaptively. Instead of applying one fixed filter, our pipeline first analyzes each image and then applies the right corrections, like balancing colors, fixing shadows and highlights, or enhancing contrast. This ensures that what we extract is the true skin tone, not something skewed by bad lighting or background noise. After that, we use the Facer library. The Retina Face MobileNet detector first localizes the face, then the FARL-based parser performs semantic segmentation, labeling each pixel into regions like skin, hair, eyes, and lips. This allows us to isolate and analyze only the skin pixels, ensuring the accuracy of our skin tone clustering. To reduce noise, we first applied a mini K-means clustering within each face image. This gave us a small set of representative skin tone pixels per face, instead of working with thousands of raw pixels. It made the process more efficient and robust. After this, we got 10 representative colors from each person's skin tone, working in the lab color space. This gave us a feature vector of 30 values per person. To make sure these values are comparable, we standardized the entire matrix using scikit-learn's standard scaler. Without scaling, features with larger values can dominate the clustering process. By normalizing the data, we ensure all color channels contribute equally, giving us more stable and reliable clusters. In the main training stage, we applied big K-means on the scaled 30-dimensional feature vectors. We used K-means plus initialization for stable convergence and repeated the process across different K values. The final trained model was then saved for later use in our web application. Now, you might be wondering, how did we decide the best K value? To figure out the best number of clusters, we used two standard evaluation methods. The first one is the elbow method. It looks at the within-cluster sum of squares as we increase the number of clusters. The idea is to find the point where adding more clusters stops giving meaningful improvements. The second method is the silhouette score. This measures how well each data point fits within its assigned cluster compared to others, and higher scores mean more distinct and well-formed clusters. From this analysis, the silhouette score showed that K equals 8 gave us the clearest and most reliable grouping, so we chose 8 clusters for our model. So, after selecting K equals 8, the next step was to actually visualize our clustering results. Since we're working in a high-dimensional 30D space, direct visualization is impossible. To make the results easier to interpret, we applied a dimensionality reduction technique, principal component analysis. This allowed us to project the 30 features down to just 3 principal components that we can plot. From the PCA visualization, we observed that while the algorithm technically formed 8 clusters, one of them turned out to be an outlier. So, in practice, we consolidated this into 7 meaningful personal color types. Here, you can see the representative images from each cluster. This gives us a much more intuitive sense of what the clusters mean in practice. Instead of just numbers or plots, we can visually confirm that each cluster corresponds to a distinct skin tone pattern. For each cluster, we analyzed the average HSV, lab, and RGB values. Based on this, we assigned names that matches the overall visual impression. After labeling the clusters, we moved on to palette design. By adjusting hue and brightness, we created palettes that better reflect each cluster's characteristics. Finally, we manually refined the colors to complete the final palettes. For color overlay, we used bilateral segmentation network trained on Celeb A Mask HQ with 19 facial classes. The conventional method, alpha blending, gave flat, unrealistic results, especially in dark regions like black hair. To improve this, we applied soft light blending, which keeps textures and highlights intact, and sharpening to bring out finer details in the hair. Here's the formula for soft light blending, where B is the base pixel brightness and S is the blend pixel brightness. The key idea is that it adapts differently depending on whether the blend pixel is dark or light. This preserves shading in darker areas and smoothly brightens lighter regions. Compared to alpha blending, it produces much more realistic and natural-looking results. For the web application, we used a Flask backend with Python, and a front-end built on HTML, CSS, and JavaScript. Our trained ML models were exported in joblib format so they can be loaded directly inside Flask. The interface lets users upload their own images for analysis. To handle user accounts and personalization, we integrated Firebase, which manages authentication and user-specific settings. Through our research, we proposed a new personal color system based purely on skin tone, which avoids the subjectivity and limitations of traditional methods. Using k-means clustering, we identified 7 distinct personal color groups, which were validated visually with PCA. To make the system practical, we developed realistic color overlays using soft light blending, which better preserved texture and shading compared to conventional methods. Finally, we built a working web prototype where users can upload photos and test the system. Of course, there are still limitations, for example, handling extreme lighting conditions and expanding to a larger, more diverse dataset, but overall, this research demonstrates a more objective and user-friendly approach to personal color analysis. Thank you for your attention. We are Team Underdog, and this was our AI-powered personal beauty advisor project.